So today we are going to start lecture 41, and this is the final video for the chapter on constraint optimization from my book. And essentially in this video I am going to review the various methods and concepts we have learned in this particular chapter. So again I am Dr. Ranjan Ganguly. Now when we started the study on constraint optimization, we started with linear programming. And linear programming typically uses the cost function and constraints, which are both linear functions of the design variable. So essentially you can visualize linear programming as a problem where all the cost functions, all the constraints are essentially straight lines or planes, and then the optimal points are calculated using the theories which involve this subject of straight lines and planes. In many ways, these are directly linked to matrix theory. Now, one of the things we saw that the optimal points of a linear programming problem typically lie on the vertices of the feasible region. And essentially, if you have a simple two-dimensional problem, this is expressed in terms of some polygons or trapezoids, and then you need to look at the vertices of this particular polygon, and one of these will be the optimal point for this linear program, provided of course that you have properly formulated the linear programming problem. In some cases, the optimal point may be along a complete line. Now, one of the ways to find the optimal point of linear programs is to locate all the feasible solutions and then compare these feasible solutions to get the best value. And we tried this approach using some simple problems such as the profit maximization problem. Now this kind of approach works out reasonably well if you have a low number of constraints and design variables. But if the number of design variables and constraints becomes larger, you get the curse of dimensionality here, and essentially the problem becomes extremely time consuming. Therefore, in real life, methods such as the simplex methods are often used to solve linear programs. And what the simplex method does is that it moves to the vertex points which result in a maximum decrease of the objective function. And therefore, instead of searching the vertex points one by one until all the vertex points are completed, which is there in the brute force method, what you do here is that you move to the point which yields the maximum decrease in the cost function, and then very quickly you are able to converge to the actual solution of the linear program. Now the simplex method is good because it typically is more efficient than finding all the solutions, and therefore it works out well for many problems. Now of course we saw that besides the simplex method there are methods such as Karmakar's method and so on which are more fast in terms of solving linear program, but if you are interested you can refer to more books on that topic. Now whenever you have problems of less than type or such constraints, then we can use the regular simplex methods. But in many situations we have the greater than equal to type of constraints, and in those cases you need to use a two-phase simplex method because you need to get the basic feasible solutions first. Now in general, if you are using linear programs, then you don't need to write out your particular code because there are a plethora of software packages which are out there which have been used to develop these linear programming solutions. And you can use these packages to get much better and faster solutions for large size problems which are typically found in corporations and various large systems. Now we also saw that linear programs come up in certain technical fields, most likely in business and management, in chemical engineering, in supply chain, and so on, and therefore it has a lot of practical importance. Now, then we turn to the problem of nonlinear objective function and constraints. And the first thing which would come to mind is that why not use some way to convert this constraint optimization problem into an unconstrained optimization problem. And this is done using barrier or penalty methods, which typically use barrier or penalty functions. And essentially these functions put a penalty on violation of the constraints. So the penalty function is a composite function of objective function and constraints. Now, when the constraints are not violated, there is no penalty. When they are violated, there is a penalty. So this constraint violation is penalized through a penalty term, which is superposed onto the cost function term to create this composite function. Now, beside penalty methods, which typically move in from the infeasible region into the feasible region, the barrier methods essentially create composite functions so that the design variable stays inside the feasible region. So you can look at these methods as creating a high barrier or a wall surrounding the feasible region, and then the design point cannot escape from the feasible region. So as it nears the boundary of the feasible region, the barrier becomes very high and the composite function becomes very nonlinear and very high at this point, and the optimizer you are using will push you back into the regular zone. Now both the barrier and penalty methods are used in conjunction with one of the routine methods which we have studied before. So you can use them in conjunction with all the unconstrained optimization methods such as the conjugate gradient method or the quasi-Newton methods. Now in the penalty method, the starting point can be infeasible. And this is important because in many cases, if you randomly select a starting point, you would not get a feasible point. So in many practical situations, a randomly selected design point would be out of the feasible region, and in all those cases the penalty method can be used. But the barrier methods require you to start from the feasible region. And this is sometimes complicated because you need to find a point which actually satisfies all the constraints. And this is not sometimes easy to do because you need to find a point which satisfies certain nonlinear constraint expressions. And this itself may be a subproblem which is quite difficult to solve, and you may require the help of various numerical techniques to solve this problem. Now, you can understand from our previous study that penalty and barrier methods would develop numerical problems near the boundary of the feasible region because the function is becoming very nonlinear here. That is the composite function containing both the cost function as well as the constraints which are included in the penalty. So you may get ill-conditioned H matrices and so on, and therefore, as you know from various methods, that this can cause problems in your gradient-based methods because typically they require the H matrix to behave well, to at least be positive semi-definite near the minimum point. And most of the time the minimum point is going to lie on the boundary of the feasible region. So this is exactly where the penalty and barrier methods do get into problems. So there is a kind of contradiction here and a kind of catch-22 situation. Now, one of the reasons for the resurgence of penalty and barrier methods has been the widespread use of gradient-free methods in the past many years. Now, gradient-free methods typically include the plethora of stochastic optimization methods which have come up, such as genetic algorithm, particle swarm optimization, and so on. So again, in those methods, you do not use gradient information. You just use the function values calculated at various points in the domain, and therefore the penalty can be used without much of a problem. Now when we turn to more methods to solve constraint optimization problems, two simple methods come to mind. One would be that we could express a nonlinear optimization problem as a sequence of linear programming problems. And this is the philosophy behind the sequential linear programming method. And in this method, the selection of move limits becomes particularly important because you need to have restrictive move limits which make sure that your function is more or less linear in the region where you are considering this problem. Now, a more realistic extension is to consider a quadratic program, which is a constraint optimization problem where you have quadratic objective function and linear constraints. So this is a more realistic scenario because in a neighborhood of a given point xk, you can consider the function to be quadratic, and therefore this would represent many actual situations. Now we saw that the QP problem can be solved using a method which is based on the KKT conditions. Recall the KKT conditions can be used by forming the Lagrangian using the cost function and the constraints, the Lagrange multipliers and so on. And then we can use the simplex method to actually solve the QP problem. Now this is important because QP subproblems are used in some constraint optimization methods. For example, we saw that the constraint steepest descent method uses quadratic subproblems in conjunction with the Shanichny descent function, and this descent function is calculated based on Lagrange multipliers which go into the penalty parameter, and of course the penalty function which records the maximum violation of a constraint. So in summary, I would say that there are a plethora of constraint optimization methods, and we have just touched a small number of methods here which give you a flavor of these concepts. There are many software packages which have been developed for gradient-based constraint optimization methods, and there are go-to tools as far as these methods are concerned. So again, in many cases, you may be using these methods in your day-to-day design life, but it is always a good idea to know some basic background about constraint optimization. So again, the basic difference between unconstrained optimization and constraint optimization would be in how you manage the constraints. And very often, the optimal point lies on the boundary of the feasible region. Therefore, the choice of constraints becomes very important. We also saw that there is a trust region type of thinking which can be used to develop methods. Now, the trust region method can actually be thought of as an unconstrained optimization method, but the one-dimensional search is essentially replaced by this concept of a region of trust. And essentially, therefore, this problem about how much to move in the design space has been expressed as a constraint on the problem. And therefore it can also be thought of to be a constraint optimization method, with the constraint being essentially put on this region of trust. Now this particular concept is important because the modern trend in optimization in many disciplines is to develop some kind of meta models or surrogate models for your problem, and then to find a region of trust where this particular surrogate model is valid, and then to minimize the function in this particular region. So that is the topic of response surface method, which we are going to cover in detail in the next chapter. That's chapter 6 of my book. And the next many lectures are going to be devoted to this response surface method. So in this particular method, we are going to develop theories about how we can create approximations of objective functions and constraints in terms of linear, quadratic, cubic functions, and then how we can minimize these functions in a manner which is sequential using some kind of a trust region thinking so as to get to the actual optimal solution. And one of the advantages of the response surface method would be that it decouples the analysis problem and the optimization problem. Because as I've mentioned many times, the analysis problem is actually a computer code in most cases, and therefore you do not want to try to link this computer code with large optimization software. Instead, it's much easier to extract functional approximations of this computer code and then to use these separately by using various methods which we have discussed before. So I will culminate this video here. I'll see you in my next lecture.